Okay, finally, solutions to the industrial chemistry questions. Now, this is an old exam question and a lot of writing, a lot of ideas, but if you can drill down through all the text that you get, it's actually quite a simple question. So we've got to carefully read this blurb. Chimney gases contain serious atmospheric pollutants such as oxides of nitrogen. Oxides of nitrogen are bad. One way to remove them is to treat chimney gases with ammonia. So this reacts with the oxides of nitrogen. What you need to get out of that is that nitrogen monoxide is bad and we want to get rid of it. Then how are we going to do it? Well, we're going to add ammonia according to that previous reaction. What happens if the amount of ammonia is too low? Well, if we add not enough ammonia, there's not going to be enough ammonia to react with the nitrogen monoxide. So what's going to be left in the exhaust gases, the chimney gases? Well, nitrogen monoxide. What happens if we add too much ammonia? Well, all the nitrogen monoxide is going to react, but some of the ammonia is going to be left behind. So we're going to release ammonia into the atmosphere. Once you actually figure out what they're talking about, it's actually quite simple. It's common sense. So again, it's an example of just spending a bit of time to try and get the overall sense of what they're on about. Okay, so now we're going to make ammonia using a ammonia generator. So we've got urea coming in, we've got ammonia coming out, and then that ammonia is going to go into the chimney gases. Urea and water 1:1 ratio by mass. Add heat, get our ammonia. So that's our reaction between urea and water. One-to-one mass, one-to-one mass ratio between urea and water. Well, we see we've got a 1-to-1 mole ratio is what's needed. If we add the same mass of each, which one's going to be in excess? Well, pick a random amount, say 100 grams of both of them. Work out how many moles of both of them have you got. So 100 grams of water is 5.6 moles, 100 grams of urea is 1.3 moles. So if we need them in a 1-to-1 mole ratio, clearly we've got a whole heap more water. Why on earth would we have an excess of water rather than an excess of urea? My guess is water's pretty cheap. Increases the percentage conversion. So you get more ammonia from your amount of reactant. Urea is what you've got to pay for. Water is, well, you've got to pay for it, but nowhere near as much as you would have to pay for the urea. Changing the temperature can control the amount of ammonia produced and how quickly it is produced. So high or low temperature. So what have we got? We've got an endothermic reaction. So what temperature favours yield in an endothermic reaction? A high temperature. What temperature favours a rapid rate? Because they talk about the amount and how quickly. We need to talk about equilibrium and rate. Explain your choice. Rapid rate due to an increase in the proportion of successful collisions. You know, you've got to give the proper temperature effect on rate, and then high yield because it's an endothermic reaction. Again, the way the question's set up is a little different, and it throws people when they see that question, but really, if you drill down, it is a fairly straightforward question. Question 2. A plus B gives C. It's an endothermic reaction, which we do at 1 atmosphere. Endothermic, so we do it at a high temperature, 1 atmosphere, because same number of particles on both sides means pressure is not going to affect it. Then reaction 2, and also it's not an equilibrium reaction actually. One-way arrow. That's something you need to pick up there. Reaction 2 is an equilibrium, and it's got more particles on the left, so high pressure will favour the forward reaction. It's exothermic, so we're going to reduce the temperature. We're going to use a catalyst so that we get, it's going to be that conflict between rate and yield. A high temperature is going to favour a rapid rate. A low temperature for an exothermic reaction is going to favour the equilibrium yield, so we use a catalyst to get a better compromise. So we send our gas, we're after D, we send the gas mixture through to the separation chamber and get product. Then we can recycle the unreacted reactants here, and that's going to increase the percentage conversion of B and C. It's also going to possibly avoid a waste disposal problem. So we can get that just by reading through the question. What's it actually asking us to do? Okay. How have the conditions been adjusted to maximise the efficiency of the process? 6 marks. So reaction 1. High temperature increases the rate of reaction. It's not an equilibrium, so that's all you can say. You can't talk about yield for reaction 1. Reaction 2, you've got the low temperature favouring the yield, the high temperature favouring the rate, so we use a catalyst to overcome that conflict. Reaction 2, we've got the pressure, in fact a high pressure because of fewer particles on the product side, and we recycle the unreacted reactants to increase the yield.